Hello, everyone. So my name is Lawrence. I did my PhD at a very opportune time, right after DuckDB had started. I did my PhD at CWI, and I'm now a developer at DuckDB labs in Amsterdam. So I'm going to talk a little bit about me, about this timing of when I started and what I did. Then I'm going to talk about DuckDB as a real system, but also as a research system. And then I'm going to talk about the story of sorting in DuckDB, because this was one of my research topics before concluding. All right, so about me. I did my computer science bachelor in Nijmegen, and I had some SQL there. My data science master also in Nijmegen, and I had no DB stuff, just machine learning stuff. And somehow I managed to do a PhD on database systems after that. Not sure how that happened. Well, I had a very nice professor in Nijmegen who was interested in database systems, even though there was no real course on it. And during my PhD, I also started as a software developer at DuckDB labs in Amsterdam. So my contributions to DuckDB are, well, the main topic of my PhD. So the main topic of my PhD was larger than memory query processing. And all of this went straight into DuckDB main. So I worked on larger than memory sorting, hash aggregation, hash join, and some overall memory management. And I'm also the creator and maintainer of the full text search and JSON extensions. All right, so on to DuckDB as a research system. So yeah, what I want to highlight is, like, during university, I rarely worked on existing code. I always started with maybe public static void main, and that's it. Hello world. And a lot of database systems research is done in the same way. So I saw a lot of excellent work at VLDB, and I really like everyone actually trying to do stuff in DuckDB. But there's also a reason why a lot of database research is done with a clean slate, because you can do anything you want. And sometimes that's the only way to innovate, right? You're not restricted by a database system that has made has limitations and requirements, and you can do anything you want. And that's a great way to move forward. But that's also at the same time the disadvantage, because being able to do anything you want can mean that you're not doing something realistic. So an example of this is the radix hash join, which was very popular in literature in the past 5 to 10 years. And some researchers in Munich, I actually spoke to the author today, really liked this work, and they implemented it in their database system. And they found that it wasn't better than a regular hash join. And so how could it be? There were 3 or 4 papers on this radix hash join, and they improved on each other. They all used a clean slate and a very specific data set. So they didn't have a full-on database system and not even a full-on workload to evaluate this. And that's what I really like about seeing a lot of people's work in DuckDB, what Gabor just talked about, the repository of science being done in DuckDB. I've seen a lot of that this week, and I think it gives your research a lot more credibility, and it's really cool to see people doing something with a real system. But it also makes a lot of sense if you're starting from a clean slate. So if we go back 10 years in time and you want to work with a database system, it's quite tricky to start, because if you're at a university where they have a good in-house system, you're lucky, go use that system. But the open source options, I've listed 2 here. There are of course more, but these systems specifically I've listed because they are written in old C. And if you're doing research in 2015, you probably want something better. So since 2019, for OLAP, we have DuckDB. There might be something in the OLTP space. I'm not too familiar with it, but it's really cool to see people working on DuckDB since this time. And like Gabor said, we can't merge all of the research pull requests that come in because afterwards it's our job to maintain it. And but nonetheless, we're like really happy to see all of this research because it's also giving us inspiration and ideas to on how to continue with DuckDB. All right, so now on to sorting, which was the first thing I really got my hands on in DuckDB. So I messed around like you do in a PhD for like half a year, and then you have to start figuring out what your topic is going to be. And Hannes told me we needed a parallel sort in DuckDB, and it should preferably process more data than can fit in memory. So, yeah, so this is what I started with. DuckDB could sort, and the initial version was implemented by Mark, and he implemented this in an afternoon. And clearly, Mark and Hannes had more passion for hash-based operators than sorting because those were a lot more advanced and a lot faster. So this was a very, very simple thing where you would append data to, and it did a single-threaded sort in memory. And it uses this data structure that has since been removed from the DuckDB code base. So I was tasked with writing this sort implementation, and yeah, I was starting. As I said, I didn't have a lot of database experience, and luckily DuckDB was not as big at this time because I'm very sure that my pull request that I did then would not be merged now. So anyways, it went into DuckDB. So that was my my first research paper, and I presented at ICDE in 2023 in Anaheim. And I dealt with a lot of the shortcomings that I saw from the previous implementation that Mark made one afternoon. And I really focused on making the sorting, like comparing rows, and like really the performance I focused on, and not much else. So it improved a lot performance-wise on the previous sort. It was parallel. It had a bit better cache locality, fewer branches, and it could handle larger than memory data. So as if I were just a researcher, because at this point I was already working for DuckDB, but if I were just a researcher, I would be done. I could move on to my next paper. But I had to maintain this code. And our users found a lot of issues with the larger than memory sorting. So, for example, if you had a lot of data and you had a lot of strings, the memory allocation and disk I/O patterns were awful and performance broke down. So, and also Richard, who really likes sorting, had to deal with my code, and he had to implement it in the window and the range joins. And the API I came up with as a second year PhD student was pretty awful. So he made it work. But yeah. So why didn't I find these problems during research? Well, I had just one objective, which was the performance of sorting and not much else. So the reason that these problems got found were that people were actually using it. So we had a developer using it. We had a bunch of people trying it out and running into issues that I could not have foreseen. And yeah, so I just said this. So after dealing with issues coming in for a long time, and finishing my thesis, I finally had time for the third implementation. So I've actually had the time to entirely get rid of my first paper's research project. I have taken a lot of the lessons from that research paper, and I've combined it with like a ton of practical experience that I was fortunate to get also being at DuckDB Labs, which not many researchers are fortunate that a lot of people are using their code and finding issues, because that really made it better. And I couldn't have come up with this myself. So yeah, the author of the PR claims that it tackles all of the downsides of the previous implementation. And I'm going to go over it briefly. So this is not very much a technical talk, but the third implementation, so the initial implementation used rows instead of columns as the format, because this has a lot better cache locality, and it converted the keys to strings so that you don't have branches in the comparison function, so you don't have to switch on the types. And this is all very much still there, but it also has improved a lot. So the parallel scaling is a lot better. The I/O problems that a lot of our users ran into, I've had a lot of time to think about that. I was able to come up with a much nicer design. And it's also like highly adaptive to pre-sorted data, which is also something users ran into, because if you want to sort a table that's almost already sorted, it should be faster than one that is completely random. So in summary, it's a lot better. And I made the API nicer, and I hope Richard thinks so too. But yeah, he has already integrated the new sort into the window operator. Exactly. He thinks the API is so nice, he's copied it for some of his data structures as well. So one thing that I want to highlight is the parallel scaling. So I don't have to write research papers anymore. So it will probably be a blog post, at least initially. But this improved parallel scaling is something I think is really new. So during parallel sorting in database systems, each thread would generally collect a bunch of data and sort it. And then all of the threads have sorted data, and you have to merge them. And there's the initial implementation did this in parallel using something called merge path. So this is a visual representation, and this describes how to merge two sorted runs, so just two. And the idea is that you can use binary search to search through both sorted runs at the same time to find where the merge path would intersect. And if you know where it intersects, you know that you have to merge. Like for the first intersection, you know you have to have 3 values from the red sorted run and just 1 from the blue. And if you know where this path intersects, you can intersect the different parts independently and therefore in parallel. So this was what I had in the initial implementation. But doing the two-way merge, if your data is larger than memory, causes you on every iteration to swap out all of the data to disk and back, which is exactly what all of our users ran into when they used it. So I've been able to generalize this to K sorted runs. So if you have many sorted runs, you can still do the kind of binary search through many sorted runs at the same time and fully parallelize this part of the sort without swapping out all of the data in many iterations, because there's now only one merge iteration where all of the data gets sorted fully in parallel and gets immediately streamed to the downstream operator. If you have more questions about this, I can elaborate when we chat later. And this will be in the next release, which is next week. So just to wrap up, I have to show some performance, of course. So I ran this on my laptop. I generated the line item table from TPCH at a bunch of different skill factors. And I'm comparing the old sort, which is in 132, with the new sort. And as we can see, it's almost twice as fast on skill factor 1, but it gets better as the data size grows. So it scales a lot better with more data, and being more than 3 times faster. So at the skill factor 100, it's I think around 60 gigabytes, and I've set the memory limit to 30 gigabytes. So this is twice as large as memory, and it's still sorting in 80 seconds and a lot faster than the old implementation. So wrapping up, I think database systems research, and I've seen a lot of nice things this week, has a lot more credibility when you have a real system. And I hope a lot of you will use DuckDB. I think a lot of you are using DuckDB for your research. And I think research becomes a lot better when it's used in practice. I've been fortunate that my research code could be merged into main at that time, because that made it a lot better. And I think the combination of working on this in practice and in research produced, I think, the new sorting code, which is better than either research or just software development could have produced on its own. All right. Thank you for listening.